Okay, so yeah, I think I'll pull up a little share screen here. We're going to be looking at the petrography of particles and iron spherules from the Murray Springs, Arizona Clovis Age site. So the first image will be a backscattered electron image of a particle from the more than 400 micrometer magnetic fraction obtained from the basal portion of the black mat. Everybody now knows, I'm hoping, what the black mat is. So we're going to be
basal portion. Does that mean the bottom of it, or
yes, as in the base? Basal is base,
right?
That's not the same as like basil leaves that you would sprinkle on your pizza.
Right. It's not an herb. It's a location.
It's not an herb, right? It's not. So the Murray Springs Clovis Age site showing iron spherules. Okay, so this up here is, like I said, the backscattered electron image of a particle. And if you look close, you'll see there's a lot of little round white, real light colored features in there. And then B is a magnified version of A, where you can really see these rounded light areas. And if you look really close, you'll see that there's a texture. And this is where it comes with this raspberry texture, raspberry surface texture, right?
Okay.
And then you get to see, you've got a scanning electron microscope image of one of these, like right in the middle of this image up here, B. You see this circular feature, and then now you've got a scanning electron microscope image of that down here at C. And you can begin to see that texture that's so distinctive of a framboid. And so then in D, you've got the scanning electron image of the grains very, very close. Now, the thing that's interesting about this is if you look close, you'll see that a lot of them are cracked, right? You see the fractures in them? Can you see the cracking? Yeah. Okay.
Yes, sir.
These are very little dense particles that have been subject to tremendous shock forces. And that's why they're cracked on this level, see? So this is an example of what's being referred to as framboidal iron oxide, found at Murray Springs, Arizona. This was published in by Mostafa Fayek in the Earth and Planetary Science Letters in 2012. So this very much supports the idea of an impact. The data obtained on the framboids from Murray Springs strongly suggest that they are not only of meteoritic origin, but that they are relicts of a hypervelocity impact. The presence of the glassy matrix, now that when you looked at the picture and you saw those round things, they were embedded in this glassy matrix, right? That's important. Cosmic dust continually falls on the Earth's surface. It is made up of extraterrestrial particles, such as interplanetary dust particles and micrometeorites. These particles can consist of smooth iron, silica, and glass, and framboidal microspherules, and particles in a crystalline matrix. Framboidal magnetite has in fact been reported from chondritic smooth cosmic dust. To our knowledge, however, framboidal magnetites, such as those reported here, have never been reported in a glassy matrix in cosmic dust. Now, what he's referring to there, cosmic dust, is this constant, gentle rain of cosmic material down onto the Earth. A lot of the critics of the impact hypothesis have tried to explain away the presence of these impact proxies by saying they are part of this constant, gentle rain of very small microscopic particles, cosmic particles, raining down upon the Earth. Thus, the particles described in this study are not consistent with samples from either terrestrial or unmodified extraterrestrial sources. Therefore, as the framboidal magnetites in a glassy matrix reported here are consistent with those found in some chondritic meteorites. While I continue on with this, Mike, why don't you look up a chondritic meteorite so we can define that for the listeners so they understand what a chondritic meteorite is?
Yeah, I've heard them call them carbonaceous chondrites.
Yes,
Is that right?
Chondritic, chondritic or chondrite. Like just look up chondrite. So, therefore, as the framboidal magnetites in a glassy matrix reported here are consistent with those found in some chondritic meteorites and inconsistent with known terrestrial sources. It is possible that they could have formed as the result of the high energy destruction of an appropriate chondritic meteorite. Together, these data suggest that the framboid particles are the product of a hypervelocity impact event. Its spatial extent remains to be determined. So I think the answer to your question is that they would have been brought in by a meteorite, and in the process of this hypervelocity impact and the explosion and the violence of the explosion of this chondritic meteorite is where you begin to see the shock effects, the microscale shock effects.
Okay.
Analysis of the data presented in this paper clearly shows that the framboidal particles obtained from the Murray Springs site are not consistent with known cosmic dust or terrestrial materials. These particles occur in a glassy matrix with an unusual chemical composition. They are structurally complex and contain significant internal layering and strong fracture patterns. Such fracturing could reflect shock damage that occurred during an impact event. These data suggest that the observed textures are not due to hydrational expansion, that is, by taking on moisture, but to a shock event that fractured and largely amorphized the grains as a whole and melted and contaminated the matrix. Therefore, we argue that these particles are the product of hypervelocity impact event. The exact nature of this event and its spatial extent, however, remain to be determined. So this was in 2012. Look at this. Yes, we are viewing my screen. Look at this. Yes, 700-gram individual of the, let's see, NWA 869 meteorite chondrules and metal flakes can be seen on the cut and polished face of this specimen. So it says this is an ordinary chondrite. So Mustafa Fayek is saying that these particles that he's examining would be consistent with delivery of the infall of a chondritic meteorite, and then subject to the tremendous shock forces that would accompany. And of course, the point is, because where is it found? It's found at the base of the black mat. So that puts it right smack there at the Younger Dryas. So Younger Dryas Boundary, I'll say, the onset of the Younger Dryas Boundary. So one of the other really interesting and important studies that came out in 2012 was by Ted Bunch and 17 others, all who are members of the Comet research team. And it was published in the Proceedings of the National Academy of Sciences. It came out on July 10th, so we're moving through the year. The title of their paper was Very High Temperature Impact Melt Products as Evidence for Cosmic Air Bursts and Impacts 12,900 years ago. And so they go on to say that it has been proposed that fragments of an asteroid or comet impacted Earth, deposited silica and iron-rich microspherules, which we were just looking at. That's what we were just looking at in the graphics, and other proxies across several continents, and triggered the Younger Dryas cooling episode 12,900 years ago. Although many independent groups have confirmed the impact evidence, the hypothesis remains controversial because some groups have failed to do so. We examined sediment sequences from 18 dated Younger Dryas boundary sites across 3 continents, which included North America, Europe, and Asia, okay, spanning 12,000 kilometers, okay, around nearly 1/3 of the Earth. And 12,000 kilometers is right about 7,200 miles, okay, spanning 12,000 kilometers around nearly 1/3 of the planet. All sites all sites display abundant microspherules in the YDB, with none or few above or below. In addition, 3 sites, Abu Huraira in Syria, Melrose, Pennsylvania, and Blackwell, South Carolina, display vesicular, meaning vessels, right? Just like you would find in Escoria, volcanic rocks, right? So they display vesicular, high temperature, siliceous, scoria-like objects, or SLOs. So here's another, insider term we can use, SLOs. But here we've got the scoria-like objects. So there's vesicular. Beautiful. Yeah, look at this. And so these are produced from melting. And, when it crystallizes, you've got the gases inside, they can discharge, the volatiles can discharge, leaving the Swiss cheese effect. I think we did look at some of the objects from the very high temperature impact melt products. Yeah, I believe we did briefly look at this last week, right?
Yep.
Yeah.
We did.
Okay, so there you go. At the top are your SLOs, your scoria-like objects, and at the bottom are your magnetic spherules. So these are the fingerprints that we're talking about. Fingerprints of catastrophe. To me, what we do is we look at the fingerprints and we look at the footprints. This is from Melrose, Pennsylvania here. And cluster of oblique impacts on a scoria-like object, or SLO, that produced raised rims. So, in other words, even on a micro scale, you still got all of this stuff, under extreme high pressure, velocity, crashing into each other, right? It's part of what's going on in this maelstrom of violent, in this violent plume of impact generated stuff that's going on in the atmosphere, right? So when you look at here, like one, it's pointing to the raised rims, just like you would have with a larger crater on Earth. You have these raised rims. And it says tiny spherules formed in most impact pits together with irregularly shaped impact debris, which is number 2. Now, when we go to B, this is interesting. This is from an Australasian tektite, which is about 700 and some thousand years old, just by comparison, right? Oblique impact produced a raised rim, which is number 1. And then you have right here a tiny spherule in the crater bottom. Now, I want you to look at this oblique impact, the shape. Is with a raised rim on one side? Does that kind of, does that look familiar? Have we seen anything like that anywhere?
Oh, yeah.
Somewhere near George Howard.
Cheese.
Somewhere. Where is George when we need him? Yeah. I mean, look at this. I mean,
right away you see that.
Right. And this is probably the object here, which is actually preserved, coming in from this way, producing an oblique impact, and then downfield is the raised rim. So, yeah, this is highly suggestive. It's like a micro scale Carolina Bay.
Yeah.
So if someone were to dig next to that raised rim in a Carolina Bay, maybe the object would be there.
Yeah, find a giant ball down there. Yeah.
No, because probably if those are, and we're going to get back to that, we're going to have a whole couple of episodes about the Carolina Bays. If they were impact produced rather than ice boulder produced, or some of the other theories, the impact would likely have vaporized on impact.
Right.
Or maybe not even. See, and here's the other thing that I raised a question of when we kind of briefly touched into the Tunguska event, which obviously we're going to come back to. Under the epicenter of the Tunguska explosion, there were shallow elliptical craters where they produced somehow by the pressure striking the ground. I don't know. But there are features there.
Shockwave or something.
And what?
The shockwave maybe or something.
Yeah.
I don't know.
Yeah, they called them the cauldrons.
Well, the whole area of 200 square miles that was pretty much incinerated under the blast zone was what was called the cauldron.
Oh, okay. All right.
Right.
This is like scale invariance, though, right? This is these tiny impact craters.
Yeah, here you go. Yeah,
Yeah.
it is very much scale invariant stuff. All right, then we go to this. This is, again, a scanning electron microscope and backscatter image of collisional particles. So now here, look at this over here on the left. Now this is back from Lake Cutzio in Mexico, right? So here you have, and notice the scale down here, 20 micrometers, right? So these things are tiny. Here's two spherules that collided in flight, and then they fused together. You see that?
Yeah, that one on the left there looks a lot like when you see those images of the atomic bombs detonating, when they're first right in the very beginning.
Oh, yeah.
It kind of looks like that with the shell.
They certainly
multi-layered. It's weird.
Here's what they're saying, that the left spheral, and you can see this kind of depression around it like this. They're calling that plastic compaction to form a compression ring. So during the impact, one of them sort of was compressed, collapsed on itself, and it formed this trough, if you will.
Right.
So that's what number 1 is pointing to. And then number 2 is another compression ring. And then number 3 is pointing to a line of gas vesicles right here, and a splash apron, number 4. So if you look closely here, you'll see that there's like melted stuff that kind of went splooged outwards as a result of this high velocity collisional impact of these two microspherules. So that's called a splash apron. So another cool new term for
I'll
us.
have to remember that.
Yeah. B is Kimball Bay. Collision of 2 spherules destroyed 1 spherule. So here you can see number 1 is a spherule that's been destroyed, literally destroyed because of the violence of that impact. And formed a splash apron on the other, which is number 2 is pointing. Here's the splash apron. You can see it right here. If you can hopefully see my mouse, number 2 is pointing to the splash apron. This destructive collision suggests high differential velocities of tens to hundreds of meters per second. So that's pretty darn fast.
And the pattern on that on B there, that you up to the left of this and up above the splash apron, you can see this kind of
turtle shell
pattern. It's
interesting.
Yeah.
Oh yeah, right. Exactly. You can see that. And that is most likely the result of the fact that for a very short period of time, the surface of this thing was molten, and then it was rapidly quenched.
Right. It was
formed this pattern. Yeah.
Yeah.
So are they mostly hollow? Because that one that's impacting, you can see the interior.
Yes, not mostly hollow, but some of them are hollow. And I don't know in this case, maybe not. But this the
one that got destroyed was definitely hollow. Maybe the other one's
solid. That's really cool.
Yeah. So this right here, notice this coming down here. Here's you've got this stuff coming down this way. So all of this right here was part of a microspheral, and during the impact, it was destroyed. Presumably, the one that wasn't destroyed was of a higher density, maybe with a slightly different composition. So it was not destroyed. Now let's look here.
Talk about scale invariance. Yeah, I think somebody was looking at images like these when they hypothesized that the moon had a second object come up and attach itself to it and kind of overlaid part of the sphere that was already there. I don't know if you've seen that.
No, I haven't seen that, Brad.
Yeah, I think they were looking at pictures like this and got that idea.
Huh.
I'll share that with you.
Okay, yeah, because there,
basically what he's saying is talk about the moon. I think that's what he's saying.
One day,
subtle.
One day when the world is ready, we will talk about the moon.